My name is Noah Hughes. It says meteorology instructor, and I do teach meteorology here at the college. I also I consider myself an earth sciences instructor, and the earth sciences is geology and meteorology and oceanography and even a little astronomy all rolled up into one field. And as a matter of fact, a lot of colleges nowadays they're starting to merge their geology and meteorology and oceanography programs into something known as earth system science, because the more we learn about the earth, the more we realize you can't really separate it out into these, the solid part and the watery part and the gassy part, and they all sort of operate and interact with each other. And so we sort of look at it from a systemic whole. So I'm really an earth sciences instructor. My degree is in geology. That's why I have this little thing down here. It says not a real meteorologist. However, when I was in undergrad and graduate school, as I was working towards my degree, both my bachelor's degree in geology and also my master's degree in geology, I would petition the college to allow me to take meteorology classes and count them towards my degree, because I wanted to be a teacher, not necessarily a geologist. And so they were always pretty cool with that. And so I have taken quite a few courses in meteorology over the years at the undergraduate and graduate level. So, so I think I'm okay, right? Yeah, okay. We'll be the judge, right, by the end of the night. We'll see. Anyway, some thanks to, you can see I've got a few little blurbs up here. It's hard to see it, but the MAPS logo is up there, and that's my shout out to my MAPS committee out there that makes everything happen. They get the speakers, we recruit the speakers, they're the ones that host them and make all the arrangements and do all the advertising and all that stuff for the speakers. So, and I know there's a few members out there tonight, so thanks to them. Also to the Title V Grants Office here at Modesto Junior College, and in particular, good old Title V grant P031S090088. Which is the grant that is funding our maps. So yes, thanks to the grants department. And then of course to the college as well. So what I want to do tonight, okay, is the title says the crystal ball, which is what I tell people when they call me up and they ask me, what's the weather going to be like? I have a lot of friends that do that. Many of them are farmers and or skiers, and a lot of them are both. I get a lot of text messages from these guys, hey, is it really going to rain this much, or is it not going to rain, and what's going on? And I always say, well, let me go check the crystal ball. And it's a metaphor, of course, but by the end of the night, I'll show you what I mean by the crystal ball, and I'll show it to you. And if you're interested and want to stick around afterwards, I can even sort of give you the web address, because as it turns out, the crystal ball is online, like everything else these days. So anyway, so what I wanted to do is I want to start out giving you just a little bit of background information about some weather phenomena that operate at the large scale. There's so much to talk about in weather. Starting in January, I'm teaching an entire semester course just in meteorology, and so of course we can't do it here in a 50 to 60 minute talk. Which is about what this talk will be. So if you have any questions, we will be doing questions toward the end. I really want to leave a lot of time for that, because I have a feeling that there's a bunch out there. So anyway, we're going to start off with some of the basics, concepts behind weather, how it works. And then we're going to focus on really the simple concept of clouds and storms, and really how to make clouds, how to make storms in the atmosphere, and then how do we know when that stuff is going to happen. Okay, and that's really what we're going to focus on. Then we'll get into forecasting, how that stuff happens. We're going to talk about old school forecasting, new school forecasting, and then we'll take a look at the current forecast, and we'll see what's going on out there right now, and maybe even take a long look out and see what the thinking is for this winter in particular. One of the first things, and this is the bane of my earth science students now, I could almost hear some of them groaning when I threw this up here. This is a surface weather chart. Right here, okay? Now, a surface weather chart is just any sort of map that has weather information on it in one form or another, okay? And it shows the conditions at the Earth's surface. Now, later on, I'll show you what's called an upper air chart, and those are showing conditions up higher in the atmosphere. So what this chart is showing us here is what we call pressure patterns in the atmosphere. Whenever you watch weather on TV, how many of you guys make a habit of watching TV weather? How many of you guys watch channel, let's do a quick poll. How many of you guys like the channel 3 weather folks? Okay, all right, how about channel, what is it, CBS channel 10? No, less? Okay, what about 13? Is that ABC? Okay, so like, who's on ABC? I don't know. I don't know. I watch Mark Finan. He's my guy, kind of. I like Mark Finan. But anyway, so when they're talking about a storm coming, you'll often hear them use a lot of different terms. They might say this system, or this low pressure system, or this cold front. One term that they really never use, which is something that, I don't want to say real meteorologists, but people who aren't on TV use, the term is cyclone. Okay? A cyclone refers to any area of the Earth's atmosphere where the atmosphere weighs a little bit less. Okay? As it turns out, the atmosphere exerts pressure. Okay? It exerts pressure just like in the air, which is something, that's the first thing I have to get my students to understand, is that air is actually something. That there is something between you and me. Okay? There's a couple ways you could convince yourself of that. All right? First of all, if there wasn't any air between you and me, right? Okay? And then the other way is, of course, you can just go like this, and you can feel that there's something. Well, you're not touching your face, but you can feel that something is hitting your face. And those are gas molecules, nitrogen, oxygen mostly, some water vapor, some other gases sprinkled in there. So that's air. Okay? And air is a fluid, which means you can move through it. Okay? It changes shape. Okay? So it's a lot like water in that respect. And just like water, it exerts a force on you in all directions. Okay? Well, not me. Just you guys. No, I'm just kidding. All right, so anyway, so when you swim to the bottom of a swimming pool, you know, if you maybe you haven't done it in a while, but maybe you remember when you were younger and you'd swim to the bottom of a swimming pool and you can feel how the pressure increases on you. You kind of feel it pushing in your ears and your eyeballs and stuff like that. Okay, that's hydrostatic pressure pushing on you. The air does the same thing. You're at the bottom right now of a swimming pool that's about 100 miles thick, full of air. Okay? And it's exerting a force on your body that averages around 14.7 psi. Right? And you know PSI, pounds per square inch. When you pump up a tire or something or a ball, it has to be at a certain pressure. Okay, 14.7 pounds on every square inch of your body. Okay? You don't feel it because you're used to it. All right? But that's why, and your body's used to it too. That's why if you somehow get ejected out into space, you know, you have this tendency to sort of expand rapidly, or explode, in other words. Because your body has 14.7 pounds of pressure pushing out all the time to balance it out. Okay? So anyway, as it turns out, that pressure, that 14.7 psi, varies a little bit with time. Sometimes it's a little more. Sometimes it's a little less. That is due to differences in pressure in the atmosphere. Okay? This map is showing us those patterns in the atmosphere. These are very large-scale patterns, and that's kind of what we're going to be focusing on today, although these patterns can exist over smaller scales too. So what we see here is a map of the United States. There, here is my... here's an area of low pressure. So what this means is that people who have a device for measuring air pressure, it's called a barometer, okay, near Michigan and Illinois and this area here, these folks are reading a little bit less pressure. And by the way, you'll notice that the units up here, they're not in PSI. We use different units. They're called millibars. It doesn't matter. They're just different units. The average pressure at the Earth's surface in millibars is about 1,013, a little over 1,000. If it's under 1,000, then you've got some serious stuff going on. So anyway, areas of low pressure. So you can see these lines are called isobars, and they show us, they connect points of equal pressure. Okay, so when you draw isobars onto a map, you can start to see the pattern. Okay, you can tell that there's higher pressure here over Alberta. Isn't that Alberta? Yeah. And then lower pressure here over the upper Midwest. And okay, so high pressure, low pressure. All right. Now these other little guys, these little symbols here, these are showing us the wind. And they're giving us speed and they're giving us direction. Okay? And the way that the wind works with these little arrows is that this arrow right here is indicating a wind going this way, okay? It's going that way. A lot of people want to say, oh, it's like a weather vane. It's going, no, it's this way, okay? And then the number of decorations on it indicates how fast the wind is blowing. Okay, so these are just little codes, just a little bit of code, little symbols up there. And you can sort of see that there's a pattern here, huh? Once you start to see that this one's going this way, that one's going that way, and this one here is going this way, and this way, and this way, you could start to see that around this low pressure system, that wind is moving counterclockwise and inward. It's converging towards that low pressure. Okay, as it turns out, these differences in pressure are what cause air to move. Okay, and if you want to understand the weather, you've got to understand how the air is going to move. All right, so counterclockwise and inward around low pressure. Okay, and then if you go over here and look at the high pressure, notice that the wind is kind of blowing away from it a little bit across those isobars, but also away and in a clockwise fashion. Okay, it's hard to visualize this, so here's a good way to do it. You can take your hand, okay, and set it on any flat surface like this. Okay, and if I take my fingers, if I start off, and I'm going to model a low pressure rotation first. We call it cyclonic motion in the atmosphere, counterclockwise and inward. I take my hand, I lay it flat on a surface. I start to rotate it counterclockwise. As I do so, I draw my fingertips inward. Okay, go ahead and do it. You got a little flat surface there. Put your hand down flat. Rotate your hand counterclockwise and draw your fingers in as you do it, like this. Okay? And the reason why I'm asking you to do this is because in order for you to do it, what do you have to do with the palm of your hand? You have to lift it up, right? Okay, you have to lift up the palm of your hand. What that means, and this is important, what that means is that as air converges around low pressure, it rises. Okay? Now keep that, just put that away in your head for now, okay? Air converges inward toward low pressure, okay? Or if you want to think of it in terms of physics, you can think of it this way. Air is accelerated away from high pressure towards low pressure, all right? The reason why it doesn't go straight towards low pressure is because of this thing called the Coriolis effect, which you can ask me about later on. It's kind of confusing, but it causes things to miss to the right of their original direction. So that's why everything's going towards the low pressure, but always missing a little bit to the right from its perspective. So you get the swirling inward pattern. I'll show you some satellite images of it later. Maybe you saw some of these patterns earlier in the image up there. Okay, and so high pressure. Model high pressure. Take your hand, start with it like this, and then you move your fingers outward, clockwise, outward, and notice that your palm goes down. It's the opposite motion. Okay, that's what happens around high pressure. So in high pressure, the air at the surface is moving clockwise and outward, but what that means is, here's this high pressure, right? And so the air is all moving away from that area of high pressure. So wait, air is moving away? Does that mean that everybody here in Calgary is dead? No. What it means is that air is sinking down to the surface to replace that air that's spreading out. So around low pressure, air is spiraling inward and coming up. Around high pressure, air is spiraling downward and out, clockwise, okay? But it's that vertical motion that's really important, and I'll explain why in a second. So these are what we call surface pressure patterns, okay? These pressure patterns arise due to differences in heating of the Earth's atmosphere. Okay? Land heats up faster than water in different parts, in areas near the equator get sunlight more directly, and areas near the poles get it at lower angles. And so there's all sorts of reasons why the Earth is heated unequally. Okay? Those differences in heating cause differences in pressure. Those differences in pressure cause wind. Okay? And wind is really what makes the weather. So this is an upper level chart. Okay? Upper level charts look a little different, but they're still showing the pressure patterns in the atmosphere. It's still kind of the same idea, but here things have a little bit more of a wavy look to them. This is in the upper levels of the atmosphere. About I don't know what this chart is showing us. This looks like this is maybe a 500 millibar chart. So this is showing us the air pressure that's up at around 25, 30,000 feet high, somewhere around there. Okay, up where jet planes would fly. Okay, and again we've got our little wind symbols on here. Okay. And notice that instead of having these bullseye patterns like we tend to have at the surface, up here in the upper levels, we have this wavy pattern. We have what we call ridges, and we have troughs. Okay? Here is why upper level winds are important. Here is why when professional meteorologists sit down at the beginning of their day with their cup of coffee and they turn on their computers, the first thing that they go to is the upper level winds. Okay? The reason why is because upper level winds steer and control those surface pressure systems. Okay? You want to know where that low pressure system is going to go? You have to look at the upper level winds. So they steer and control pressure systems at the surface. Okay? So if you want to know where a storm is headed, you got to look to the upper levels. Now that might seem kind of simple, but let me show you. Here is a map showing predicted upper level. So in this case here, this is a little bit different. This is showing us the black lines are actually the surface pressure patterns, but I'm interested in the color bands. Those are that's the upper level pressure patterns on here. Okay? And interestingly enough, the cooler colors are associated with cooler areas of the atmosphere. The warmer colors are associated with warmer areas of the atmosphere. But what I want you to notice is that the ridge, and by the way, this is a huge area. This is half of the Earth, or half of the northern hemisphere right here. So just to orient you, here's Alaska. See the white here? That's Alaska. Here's Canada, Hudson Bay, and here is the lower 48. There's Florida, and here is California right there, okay? And so as it turns out, you can see that these troughs, like this one right here, some of them are kind of saggy, some of them are kind of flat, okay? Same with the ridges, they look different, so it's different all the time, and then they move. They sort of propagate like this, okay, around the entire planet, okay? And as it turns out, the area where these colors are really packed in closely together is the area where the upper level winds are strongest, and we call it the jet stream, and that's really what we want to focus on to understand the weather, is understanding that jet stream. It's basically where the green is here. Okay? Those are the areas where the winds are going to be strongest. That's where storms are going to be formed along and steered across. And in particular, storms love to form on the right side of upper level troughs. Okay? On the right side. So when you look at those upper level patterns and you want a storm, this is the area right here. It's east. The east side of these upper level troughs. You can sort of draw a line down through it like this. This is called the trough axis right here. And to the right of the trough axis in here, this is the area where surface low pressure systems develop. Okay? Remember I told you the upper level winds, they steer these surface pressure systems, but they also control their development. They're kind of like parents. They kind of try and steer and nurture you. And they can either do a good job of it or maybe not. So anyway, as it turns out, on ridges, right, like this, the right side of the upper level ridge axis is an area that is not conducive to cyclone development. It's conducive to high pressure. Okay, so high pressure systems tend to develop and form here. Low pressure systems tend to develop and form here, okay, at the surface. So that's kind of the relationship between the upper level winds and the surface winds. So you got to know all that stuff, okay, to sort of, it's kind of the background knowledge that you're going to need to know to follow sort of the rest of the talk today. All right, so why all this talk about wind? Okay. Well, as it turns out, like I mentioned, we want to focus on those surface low pressure systems because that is where air rises. Okay? And let me show you why rising air matters. What I've got here is a 2-liter bottle, regular 2-liter bottle, and there's a little bit of water in there. Can you see the liquid water that's in there? Okay? And so what that means is that the air that's inside this bottle, the water is going to evaporate into the air that's in here. And so the air that's in here is really close to saturated with water vapor, with evaporated water, what we call water vapor. Okay? You can't see it, okay? But what I'm going to do is I'm going to make a cloud in here. Okay? And the way that I make the cloud is somewhat instructive about how clouds form, right? Because if you want to have a storm, all right, the minimum requirement for a storm is to at least have some sort of cloud with it. Okay? So let's go ahead and make a cloud. Okay? So what I'm going to do to make a cloud here is reach in my pockets. Let's see, lighter. Not what you're thinking, okay? And what I'm going to do, watch carefully. No, it's really not what you're thinking. I know it looks like that. You have to roll, I swear, you have to roll the paper up to get it to smoke just right, okay? So now what I'm going to do is I'm going to push down on this 2-liter bottle, hold this smoking item up to it, and then sort of, well, okay, take a hit. Okay, that's what I'm doing. I just inhaled a bunch of smoke into there, okay? I'm going to put that out because it's bad for you. All right, now watch. Oh, no. Oh, no, there's a hole in my bottle. Can you see the cloud? Can you see it from where you are? Forming, it's gone. Now you see it. Okay? What a cloud is it's a collection of tiny, tiny liquid droplets, okay? Like that. It's a collection of many, many liquid droplets, but they interact with visible light. In other words, you can see it. When you can't see it, that's water vapor. When you can see it, what's happening is the water vapor has turned into liquid. The reason why I added the smoke is because water molecules need those little smoke particles to kind of gather around. And then they turn into tiny, tiny bits of liquid, and that's a cloud. But what I really want you to notice is when the cloud forms. Watch, when I squeeze it, cloud goes away. When I release it, cloud forms. Compression, evaporation. Expansion, condensation. So why does the cloud form when I allow the gas to expand? Okay? Well, as it turns out, when gases are allowed to expand under their own, anytime gases that are under pressure are allowed to expand, their temperature drops. And when you drop the temperature, that's when condensation happens. Cooling is what results in condensation. Okay? We might get fog tonight here in the valley and when does fog form? It forms at night, late at night, when the temperature cools down enough. Okay? That's when condensation happens. So fog is a cloud that forms here at the surface. Fog doesn't make storms and stuff. Okay? It's clouds. It's condensation that happens up high. Those are the bad boys that give us our storms. So this diagram here shows kind of how this works and why it is that we need air to rise. Okay? As air rises in the atmosphere, and I don't know if this is still going to work or not. Yeah. As air rises in the atmosphere, it experiences less and less pressure. Okay? And you've noticed this before. When you drive up to the mountains, how many of you guys have ever driven to the mountains? Thank you. Good. Okay? When you drive up to the mountains, sometimes your ears kind of pop, right? Sometimes your bags of potato chips, because you always bring potato chips to the mountains, right? You gotta. And the bags, they inflate, right? You ever noticed that? Those bags, they just kind of puff up really big. That's not because there's some magical elf that's inflating those bags of potato chips in the back of your car. It's because there's less pressure on it. So any parcel of air, we call them parcels, any blob of air that rises up in the atmosphere is going to expand. And when gases expand, they cool down. Okay, you can convince yourself of that too. You can, shaving cream, right? Sprayed in your hand, that's an expanding gas. It's always kind of cold, no matter how warm your bathroom is. It starts off kind of warm, spray it in your hand and let it expand. It's always cold. Expanding gases always cool down. Okay? CO2 cartridges, that's gas under pressure. You go paintballing with your friends, unload on your buddy, pop that CO2 cartridge out and you can't even touch it, huh? It's so cold. Okay, so anyway, rising air expands and cools, and it actually cools at a pretty known rate. We don't need to get into that, but eventually it'll cool down enough, what we call the dew point. Okay? The height at which that happens is called the condensation level, but you don't need to know that because there's no test tonight. Okay? But anyway, that's how you make a cloud. Okay? You got to get the air to rise. All right? So those are some basics. Low pressure systems, the air converges and rises like that. That happens on the right side of upper level troughs. Okay, so right side of I keep going like this, but I should be going like this, huh? On the right side of upper level troughs, that's where surface low pressure systems develop. Surface low pressure systems involve cyclonic motion in the atmosphere where winds converge and that forces the air upward. Where air is forced upwards, that's where we get clouds. And that's the most basic minimum qualification to be a storm that you need. Okay? Everybody good on that? All right, let's move on then. These are some pictures of clouds from some of my meteorology students. The kind of lifting that happens gives you the kind of cloud that forms. So these are some what we call stratus clouds. There's kind of a couple layers, like the sort of flat clouds. When you lift a whole layer of air at once, you get a whole layer of condensation, and you get a kind of cloud called a stratus cloud. Sometimes you can get clouds like this, which are sort of like puffers, but they're way up high. They're called alto cumulus clouds that are up there. And so sometimes meteorologists refer to this as mackerel sky. The previous two photos were taken by a student named Casey Nee. In my meteorology class, we have photo contests. So whenever weather starts happening, we'll have the photo contest, and people send me photos and get credit for it in class. This is one taken by William Haas. I really like this picture because it's very Modesto. Something about it's just like the palm tree and the other, I don't know. But these are what we call cumulonimbus clouds. Which cloud looks like it's more likely to produce rain? That one or that one? This one, huh? Yeah, you already know a lot about weather. You know the big, scary, dark clouds. As it turns out, the difference between a little friendly, little puffy cloud and a big, scary, puffy cloud, which is, by the way, it's called a cumulonimbus, the difference is how cold it is way up high in the atmosphere. When you lift a parcel of air in the atmosphere, it'll continue to rise as long as it's the warmest thing around, right? Because warm air rises. And so if it's really cold up in the upper levels, it's really easy for these rising blobs of air to keep rising. And the taller they rise, the bigger and scarier the clouds are. Okay? Here's some other ones. This is a photo taken by Gabriel Torrijos. And so anyway, this is another cumulus cloud. It was so big that you had to be far away to get a photo of it. This is another photo of a whole line, cumulus congestus. This is what's happening as a cold front is approaching. This is a picture. So is the one on the opening slide from my old house in Sonora. So this is a cold front that's approaching. What happens with a cold front is you have an advancing mass of cold air moving across the Earth's surface. And it forces the warm air up like a wedge. It's actually called wedging. And as it does so, you get this big line of scary-looking clouds like that, and we call that a cold front. Cold fronts are associated with low-pressure systems. Okay? So again, it's all part of that big low-pressure system at the surface. So how do you get clouds to rise? Or how do you get air to rise to form clouds? Sorry. There's four fundamental ways, and we're only going to focus on one of them, really. You know, you can heat up a little patch of the atmosphere, and that air will rise and can form a cloud. And this can happen sometimes whenever we get thunderstorms here in Modesto, which tends to be in the late spring. This is dominantly the mechanism that helps those thunderstorms form. They form on sunny days right after a storm has come through. The air is cold, the ground is wet. But the sun is pretty intense by March or April, and that's when we get the surface heating, and you'll get some rising air up into the colder air. But notice the scale here. This is a pretty small scale. That's 5 kilometers across. Another way you can get air to rise is you can have the wind blow up a mountain like that. That's why it rains and snows more up in the Sierras than it does here. Okay? And by the way, when the air comes down the other side, it tends to compress and warm. So you get the opposite effect, right? Remember, expansion happens when air rises, right, to form the cloud. But when the air goes over the other side of the mountain range, it descends the other side and compresses. And that warms it up and causes the clouds to evaporate. So that's why if you drive up over the Sierras, on the west slope of the Sierras, lots of precipitation and a temperate, forest up there. You drive over the other side, it's desert, right? Reno and from there on. So that's one of the reasons there. And so this is another important factor. This is the one we're kind of focusing on tonight, where we have areas of low pressure. The winds converge from either side because they're moving towards low pressure. And that forces the air up, and that's how we get clouds and storms. And this little cartoon right here discusses how when you have boundaries between air masses, what we call fronts, how that can produce lifting as well. Anytime you have warm air and cold air colliding, you get these large-scale effects known as fronts. So you can have lifting happening there. But again, this and this and this all tend to happen here in California in association with surface low-pressure systems. Okay? So again, so how do we forecast this stuff? All right? So there's a couple of quotes I put up here. I'm going to read the first one to you. This is by a German philosopher / scientist from the Renaissance time. His name was, I don't know how to pronounce it, Leibniz. Okay, Leibniz. And anyway, I picked this quote out just because he was an optimist. As a matter of fact, he kind of got made fun of because he was such an optimist, if you ever read Candide by Voltaire. But anyway, he said that the universe is an understandable place. And this is how he expressed it. He said, every present state of a simple substance is naturally a consequence of its preceding state, in such a way that its present is big with its future. Okay? In other words, if you look at the way things are now, they are the way they are now because of the way they were in the past. And the way they're going to be in the future is because of the way they are now. In other words, the universe is a predictable place. Okay? At least somewhat. Okay? That optimism's been tempered over time with science. But anyway, that's what it means. Every present state of a simple substance, so think air, simple substance, is naturally a consequence of its preceding state. Think about pressure. What's the air pressure like right now? Okay, that's going to tell us what the air is going to do in the future. So I've simplified this. So that's Leibniz. This is me. Okay, this is me. This is what I tell my meteorology class at the beginning of the semester, and it's a mantra that takes us all the way through the semester. If you can see the patterns of air pressure, then you can predict the wind. And if you can predict the wind, then you can predict the weather. Okay? If you can predict the wind, you know where it's going to rise. If it's converging, you know you're going to get rising air. Okay? So if you want to predict the weather, you got to understand what the wind is going to do. And if you want to understand what the wind is going to do, you got to look at the air pressure. Okay? So it all starts there. All right? So that's kind of where we're going. We're going to look at pressure patterns, okay? And understand, we're going to talk about how we measure them and how we map them out and how that leads us to an understanding of the weather. Okay? How are we doing for time? Okay, I got to move along here. All right, so anyway, there's a couple of ways that you can predict the weather. There's kind of new school and there's sort of old school. People have been predicting the weather with some amount of success for a long time. Okay? If you could predict the weather 1,000 years ago, you might end up the king or the chief or whatever kind of society you were living in. You know, so it's been a long time. If you really think about it, you can look at the sky and you can tell if a trough is approaching or not. You can tell if clouds are approaching, if a front is approaching. For instance, to the trained eye, this kind of sky right here, which you might recognize as taken from the same porch as some of the other pictures, this kind of sky where the sun is kind of looks like it's kind of smeared out. It kind of looks watery. You might even get these little optical effects over off to the side like this. These are called sundogs. These little rainbow-looking things off to the side. Sometimes you'll get one over here on the other side too. To the trained eye, to somebody who pays attention, you might notice that the sky often looks like this about a day or 2 days before a storm comes. Okay? So that's just old school. That's just using your eyeballs and your experience and your observation to predict the weather. And there's other ways you can do it too. For instance, if you want to know what's happening in the upper levels, you just got to look up at when there's some clouds that are up there, or maybe even a jet with a contrail up there. That's up high enough. Just watch which way those clouds are moving, and that's going to tell you which way the wind is blowing up there, because that's what moves clouds, right? Is wind. So if you're standing here in Modesto, okay, and you look up, okay, and you see that the clouds are moving from the southwest towards the northeast, okay, by the way, that's north, okay, that's north, that's south, east, west, okay. If you look up and you see that happening, just like this guy, here you are on your way to class, okay, right here, and you look up in the upper levels and you see, oh, Richard, there we go. All right, you see these clouds moving that way. To somebody who knows anything about the weather, you say, okay, that means that the upper level winds are moving like this. That probably means that I'm on the right side of an upper level trough. Okay? Whereas if the winds were coming this way, you might say, oh, I'm on the right side of a ridge. So just looking at the upper level cloud pattern can tell you a lot. If the clouds are moving from the southwest to the northeast, then you're in an area that's prone to cyclone development. You can expect some active weather in the next day or two. If the clouds are going from the northeast to the southwest, not so much. You're probably, the weather's probably going to clear out and stabilize because you're in an area that's conducive to high pressure development. So just looking at clouds, and again, if you think that we didn't notice this until recently, then you're wrong, because people used to live outside all the time. Okay? So people would notice this stuff, and like I said, if you could start to predict the weather, the next thing you know, you're the man or the woman. Okay? And so a lot of what I'm showing you isn't really new stuff. It's just we describe it a little bit differently. So today we take a little bit more scientific approach at it. We're more careful about our observations. Our observations are more robust, taken over bigger areas with more precise equipment and a lot more, we measure a lot more stuff in the air. We measure temperature, humidity, wind speed, wind direction, dew point, cloud cover, all sorts of stuff. And we do it, okay, so that we can produce numbers that we can put into computers, and we can have those computers help us try to predict the weather. Okay, this is called numerical forecasting, and this is the way it's done nowadays, okay? But it all starts with making observations about the atmosphere. So one of the first ways that we do it is with something like this. This is called an ASOS, A-S-O-S, Automated Surface Observation System. The closest one to our location right here is out at the Modesto Airport. We have an ASOS system out there, and it's this whole package of instruments that measures all those things I just mentioned, including visibility, cloud cover, wind speed, wind direction, temperature, dew point, relative humidity, all that stuff. And we have these things all over the place. These are all the places in California that have METAR stations. This is just one network. Okay, so we've got a very dense network. Let's go to Modesto, right there, KMOD, that's our station. And let's just see what's going on. Here's the latest time. So this observation was taken at 1953 hours. What time is that? 7:53, okay. The wind is calm, visibility 9 miles. The weather is fair, the sky is clear, the air temperature is 47. The dew point is 44, so if the air cools down to 44 tonight, we're going to have fog. Okay? Calm winds. Wait, where is it? Winds are calm. Where are the winds? Over here. Calm winds and temperature approaching the dew point. Looks like fog tonight. Okay? Here's the relative humidity there, and there's the pressure. So all that stuff. So anyway, that's an observation. Okay? We also use these weather balloons. Okay? Here's one. Okay? It's harder to take measurements of the upper atmosphere, okay? But we still do it in kind of this primitive way. We blow up these big balloons that are about this big. You want to blow this up for me, son? I'm just kidding, okay? But they're about this big. This is a weather balloon, okay? But what we do is we tie an instrument package to it, and we release it into the atmosphere. And this is done at a lot of locations all across the world, okay? All at the same time, twice a day. And that produces a vertical slice through the atmosphere. That's called a sounding, okay? And those numbers go into our computers too. And then of course we have satellites as well. So these are, this is examples of what sounding data looks like. So our closest weather balloon release location is Oakland. So if we go to Oakland here, the Oakland sounding, but this is the kind of output that you get, okay? This is temperature and this is dew point, and that up there is telling you wind. These are showing you wind speeds and directions at different heights and all sorts of other data that is listed across this area up here, okay? And so anyway, that's another way that we collect information, that we observe the atmosphere. Because again, you have to see the patterns, right, before you can make those predictions. Even the computers need to see the patterns before they can make the predictions. So another way that we make observations is weather satellites. Okay, so this is our local satellite server from our Sacramento weather office. That's the local weather service office out of Sacramento. And we can pick any one of these. I'd like to go with let's go with the 4-kilometer infrared image. And boom, right there in real time, I'm seeing there's a satellite that's in a geostationary orbit above my planet, taking pictures, beaming them down to me, to a server that's digitized and enhanced and sent to me as soon as I click a button. Okay? And so anyway, this is showing the cloud patterns. The colors represent the coldest In other words, the highest cloud tops. And so anyway, you can see that there's a few high clouds drifting through, but mostly we've got clear skies. And again, notice how the clouds are kind of moving this way. So there's a ridge right here, probably. So I bet when we look at the forecast, I bet we're going to be seeing pretty fair weather for a little bit. Okay, just based on the way those clouds. And again, if you saw those clouds moving overhead today, and you saw that they're moving this way, you could have told yourself, yeah, looks like it's going to be pretty fair weather for a bit. Okay. All right. So those are how we make some observations. So what do we do with those observations? Okay, don't freak out. Okay, don't freak out. This isn't that bad, okay? I just put this on here just to give you an idea of the kind of numbers that we have to crunch here. When we say numerical weather forecasting, we're not talking about looking at the clouds and saying, looks like rain, okay? No, we're being very quantitative about it, okay? When you say looks like rain, you're being qualitative. You're just describing it with words, but you're not being very precise, okay? When you want to know, like, hey, there is a 40% chance of showers between 9 and noon tomorrow, okay, with a temperature of 47 degrees and winds out of the south, you got to be quantitative, okay? That means you got to use the language of science, which is math, okay? And math is what allows us to do it. We develop these mathematical equations that tell us what's going to happen. Okay, these are equations that govern the behaviors of fluids. They're called equations of states or fluid dynamics equations. They're generally differential equations that you would learn how to calculate in a Calc 1. If you took a Calc 1 class, you would start to learn differential equations like this. Okay? But this is a little bit harder than your Calc 1 class because what we do is we divide the planet up into these grids. Okay? And based on the observations that we have, we populate these grids. Okay, so we tell the computer, okay, we made all these observations. Here you go, computer. The computer makes these maps, okay, of what those conditions look like the maps that we were looking at before, and then it crunches the numbers. And when I say crunch the numbers, I mean it crunches the numbers. There are so many different variables that affect the weather, but this thing, there's an equation for each one. So for each one of these little boxes that we divide the atmosphere up into, the computer has to crunch all those equations for one box, and then how it affects the boxes around it, and then it crunch the numbers for each one of those boxes and how they affect all the boxes around it. And pretty soon, you can't do it with your laptop computer. Okay? You just can't do it. You need some of the most sophisticated supercomputer equipment in the world, and that's exactly what the National Weather Service has. It's housed in, it's actually called the National Centers for Environmental Prediction. It's in Maryland, and that is where their server stacks are. These are the guys right here. This is what it looks like. That's the brain behind the crystal ball right there. Okay? And these are the equations that they're using, and that's the building that they do it in. It's a brand new building. They just moved in last month. Okay? It's in Maryland. College Park, Maryland. So anyway, what does it tell us? Okay. Well, let's take a look. So this is their how they make it available to the public. All of this stuff is done with taxpayer money. Okay, and so it's available to all of us. Okay, when you watch the news on TV and they're saying, "Oh, look at here's our futurecast tracker, triple Doppler storm 9, 7, whatever," that's not theirs. It's yours. Okay, that Doppler installation, that data, that's your data. Okay, they just they take it and they package it and they make it understandable. So I'm not saying that they don't do anything, but it's not their Doppler station. It's the government's Doppler station that's at the Sacramento airport. Okay, and they all get that data just like you can. Okay, so anyway, this is where the outputs of these computer models come from right here. Okay, so I'm going to go here to, I'm going to pick out North Pacific. That's this region, right? See that part of the world, this little box there? So then I'm going to click on the North Pacific there. And then I'm going to ask it. Then it says, okay, what model would you like, Mr. Hughes? I'll say, I think today, let's see, the GFS, the NAM, they all mean different things. But the GFS is the one that's probably the most used, okay? And that says, okay, what parameters would you like to look at, Mr. Hughes? Would you like to look at precipitation in 3 hours time slices, 6 hour, 12 hour? Would you like to look at the pressure patterns? Would you like to look at temperatures and pressure. Would you like to look at the upper air, the wind speeds, the heights, precipitable water, relative humidity? What do you want to look at? Nah, I'm just going to go look at this one right here. This is the 850 millibar sea level pressure chart, and I'm going to look at the current one right here. So this is the latest observation right here. Okay? This is what's happening right now. Okay? This is the weather balloons released, all the ASOS systems, all that stuff goes into the computer, and the computer says, okay, this is what I'm seeing right now. Okay? And again, I know it's kind of hard to look at this. Here's California right there. Okay? This is the Pacific Ocean. And again, I don't know if I mentioned it, but those upper level winds, they blow from the west to the east. So our storms tend to move from the west to the east. So yeah, sometimes from the southwest, like last week, sometimes from the northwest, like hopefully later this month. But anyway, here's a big area of low pressure right here. Okay, the black lines, these are the isobars. The red and the blue lines, those are isotherms, so those are showing you different areas of temperature in the atmosphere. So this big H is telling me that this is a high pressure system. Can you see this bullseye of high pressure right here? Okay, so there's our high pressure system right there. Now I told you that, so low pressure over here, these are the Aleutian Islands, high pressure there. All right, and let me show you the upper air chart, what that looks like right now. So let's go back here, back, and I'm going to go say, show me what's going on at the 300 millibar level. And hopefully it'll take me there, and I'll say, show me the current analysis, which is 0 time. Here it is. This is showing the pressure patterns in the upper levels, okay? And again, in this case here, the black lines are showing the pressure patterns, okay? So here's a trough. See the trough? Here's a ridge, and here's a kind of a broad trough over the central part of the country. But right now, look at this. We are on the right side of an upper level ridge, okay? Again, that's why that high pressure system is there at the surface. Remember, this is what's happening in the upper levels. And by the way, these colors, the colors are showing you wind speed, okay? What we want to see, if you want, assuming you want storms, assuming you're a farmer or a skier, or really anybody with half a brain who understands how important it is for us to get rain and snow here in California, how important that is to our economy, how much money each raindrop is worth to us, okay? You want to see the big blue worm. See this? You want to see the big blue worm extend from East Asia across the Pacific, maybe go up and over a ridge, but you want to see the big blue worm come into California, preferably as part of a trough like this. Okay? So now the crystal ball. What I'm going to do is I'm going to say, okay, supercomputer in Maryland, show me what's going to happen for the next 7 days. I'm going to say loop all. All of these are the forecasts at 3 hours time slot. So that was the one I looked at earlier, 0, 0, right there. 3 hours in the future, 6 hours, 9 hours, 12, 15, all the way up to 165 hours in the future. Okay? What's going to happen, computer? Okay? Crunch those numbers and show me. So I say loop all. And let's watch what happens. Come on, big blue worm. Oh, big ridge. Oh no, we're under a ridge still. Geez. Oh wait, there's a trough. Come on, come on. Oh, maybe. Yeah, okay, we'll take it. All right, so another ridge. Geez. Yeah. That's 7 days. So that's the next week. Mostly it looks kind of dry. We get this funky little kinked out little trough right there. I don't know about that. It'll get colder, that's for sure. Notice one thing about this. If I stop this thing, I can control this animation here. So let's watch when that kinky little trough moves over us right there. Okay, now that looks okay right there. What day is this? This is Wednesday, the 12th of, so this is next Wednesday at 0900 UTC, which is 1 a.m. local time. Okay, so this is 1 a.m. next Wednesday. Yeah, we've got a little trough, and here's the trough axis. We're just on the right side of it. So maybe there's some reason for hope. We'll look at another chart in a second that's going to show us rain, and we'll see if it's actually predicting rain out of that trough. But notice what happens on the back side of it. I'm going to go forward 1, 2, 3 more like that. Now, look at this. We've got winds coming straight down from the north, right over California. Pretty strong jet stream winds coming from the north. So that's going to mean that by the end of next week, we're going to have a little cold spell. Okay, those are some cold winds coming from the north in the upper level. So anyway, that's what the crystal ball is showing now, at least in the upper levels. So let's look at the surface. I'm going to go back here and say, okay, let's look at the surface chart again. And now loop it all. Okay, so remember, now we're going back to what's happening at the surface, not the upper levels. Here's our high pressure system. Here's our low pressure system. We're going to run it into the future here. Okay, crystal ball, engage. Science. All right, there it is. So there's our big high pressure. Oh, by the way, the green is rain. Okay, the green is where it's going to rain. Notice the association of the green colors with the big L's, right? So that's what I was talking about earlier. Where the low pressure systems are, that's where the precipitation is going to happen. So what this is showing you is the amount of precipitation that's color-coded over here in each 3-hour time interval. Okay? So it looks like, let me kind of watch here. There's our big high pressure system. Okay, stop there. I want to kind of control this animation now. Here we are. So this is next Wednesday. This is 4 a.m. next Wednesday. So here we go. This is the blue line. This is kind of showing cold air. And let's see here. So maybe next Wednesday, come on. That's not a lot of rain right there, but maybe a little bit. Certainly a little blast of cold polar air coming down next Wednesday right there. Okay. And so again, playing it in the future. Okay. Yeah, boy, that's a nice little shot of cold air right there. It's on, so notice that here's the high pressure. The storm moved up over it, down underneath it, dunked a bunch of cold air in there, and maybe produces some showers, but light. It looks like this was kind of one of those cold but not very wet storms next Wednesday, okay? And so again, then it's gone, and then high pressure looks like it's back. Oh, it's kind of teasing us there. Look at that big storm kind of coming in, but it cuts out right there. So now this thing's telling us that next Wednesday we might get some rain. What's today? Friday. Thank you. Today's Friday. So if I tell you, hey, next Wednesday it's going to rain, if Mark Finan tells you on the news tonight, next Wednesday there's a chance of rain, how certain is Mark Finan going to be that it's really going to rain Wednesday? Not so much. As a matter of fact, I bet if you watch the news tonight, because I've been watching these models all week. I watch them all the time. I'm a geek that way. This is new, that it's showing something happening Wednesday. It hasn't really been showing you this. They run these models 4 times a day, every day, based on new sets of observations. Okay? And every 6 hours, one of these new model runs comes out. And so you got to watch them over time to really decide if you want to believe it or not. And let me show you why. I'm going to show you something called a spaghetti diagram. Okay? This is showing upper level pressure patterns, but without all the lines. It really simplifies it, and it's just basically 2 lines. One there and one there. Okay, so here's a ridge right here. Here's the big broad trough that's over the central US. So it really simplifies it for us, okay? Now, if you notice, these aren't actually one simple line. There's a whole bunch of little lines. They're all packed in together. Each one of those represents a different run of the computers. Not only do we run the computers every 6 hours, we run them 20 times every 6 hours, okay? Because every time we make measurements, we don't measure the entire atmosphere. There's all sorts of assumptions that go in there. If we measure the temperature in Modesto at 60 degrees, down in Fresno at 65, you have to make an assumption about what that temperature transition is like between here and Fresno. And there's a lot of uncertainty about that. Even our temperature measurements are uncertain. So what we do is we take the measurements that we get and then we tweak them just a little bit, okay? And we run it 20 times. So each one of these lines represents a different run of the models. So you can see that for right now, things are pretty certain. We know that this pressure line is right about where it should be. It's pretty obvious that there's a trough right there. These are all the different model runs right here. Notice there's 1, 2, 3, 4. There's pretty good agreement among all the different model runs right there. Watch what happens when we play this into the future. Watch what happens. And again, keeping in mind that when these lines are close together, that means that we're pretty confident about what the weather is going to be like that day. Okay? As they spread apart, we're less confident. So what I'm going to do now is I'm going to go back and I'm going to tell it to loop the spaghetti for me, and you'll see why they're called spaghetti diagrams. Watch what happens over time. This is called chaos theory, right? This is an idea of, this is a small change today produces huge changes in the future. As you can see, those tiny differences in our assumptions about what the weather's actually like right now can result in huge changes in the future, okay? For instance, if we go to that same time on Wednesday, let me scroll forward here to Wednesday morning, okay? You can actually see that we're not entirely sure where that trough is going to be. It could be over here. It could be over here, in which case we wouldn't get anything. But what the line that we saw was the average of all of these right there. But this is why there's so much uncertainty in forecasting. It's because our observations aren't good enough yet. Okay? We need more observations. You can't release weather balloons all over the world every hour. You just can't. Okay? Over the oceans, who's going to release weather balloons over the entire Pacific Ocean? Okay, we do it in Hawaii, a few ships that are out there, and that's about it. So our data is not good enough that's going into the computer that we can't expect good data coming out. So that's why, well, 2 to 3 days in the future, yeah, you can kind of hang your hat on that forecast. But when I tell you, or Mark Finan tells you something's going to happen next Wednesday, 5, 6 days out, keep watching the weather. Okay? A lot of misunderstanding of weather forecasting comes from people who see something like that. They'll see Mark Finan and say, hey, next Wednesday, maybe something's happening next Wednesday. I'm going to put a little rainy cloud icon on my 5-day forecast. Okay? But if you don't watch the weather again for the next 5 days and Wednesday comes around and it's sunny, and you're like, that Mark Finan, that guy's always wrong. But that you're not paying attention enough. You need to watch the weather all the time because those 5 days out, you can't trust that until it's closer in the future. And this diagram here shows you why. So that's uncertainty, okay? When we talk about what this winter is going to be like, we transition from talking about weather to talking about climate, okay? Talking about weather is what we've been talking about the whole time today. Now, climate doesn't focus on one particular low pressure system. It looks at the conditions over the earth and says, how likely are you to get low pressure systems? Okay? The way I explain the difference between weather and climate to my students is I say that weather determines the clothes that you wear. Climate determines the kind of clothes that you buy. Okay? It's long-term, long range. So anyway, when we look at those conditions right now, unfortunately, look at this. This is showing precipitation chances for the 3 months, December, January, February, which are our main rain-producing months. Right now, these forecasts are looking pretty dismal for California. I don't know, I hope that's not true. These forecasts are pretty bad. What we call forecasting skill, when we're looking this far out, our forecasting skill isn't really all that good. At the beginning of December, we were supposed to have a dry December. Okay? In 1 week, we got enough rain for like 3 Decembers. Okay? So again, the farther out you go, the less certain we are. Okay? So this is a climactic outlook. So this is sort of our winter outlook right here. And this is showing the chances of below normal precipitation. So what it's saying right here is, yeah, there's about a 40% chance that we're going to get below normal precipitation, as opposed to equal chances. Okay, so that's what that's showing us. So we'll see. I hope it's wrong, because I'm a skier and I'm ready for some snow. Thank you very much.